Ready to go? Okay, we're going to get started now. Just welcome everyone. My name is Paul Stubbs. I'm a director of AI marketing. I own autonomous systems sort of strategy. And one of the things that it's really exciting this week to finally announce and talk about the things that we've been working on, and then have you guys to help me understand, where your areas of interest are. And I'll talk about kind of some of the behind the scenes efforts that went on and how we're thinking about this moving forward. This is definitely the beginning of a long journey that we're just starting this week. How many people have seen the robots over here and over in the section? Everybody? One? Okay. So today, we're living in this world that is automated, right? And sometimes we get confused at what the words are, so we're going to kind of go through how we're talking about these words. So we live in a world that's automated. In other words, if your system, your robot, your manufacturing line can do something over and over again in a repetitive fashion, and it does that very accurately, we consider that as automated. We're trying to move to a world that instead is increasingly autonomous, meaning that it understands the world around it. It's able to use sensors to perceive the world around it. It's able to plan and act upon those sensors, and it's then able to take some action into that, right? So if you think about where like IoT is sort of the first part. There are sensors, and maybe there is some intelligence there, but it's really just about sensing the world. Sort of autonomous systems really about sensing the world, planning something, and then actually manipulating or doing something in the physical world. And we're in this sort of fourth industrial revolution, they call it, right? And so we had sort of, mechanized systems through production and manufacturing. Then we went through sort of kind of where we are today, which is things that are powered by software, right? They're automated by softwares controlling them. They may also be manually operated, right? We have a lot of cases that's the case. And we're really moving into this world where things are autonomous. Things are happening more on their own. They're more independent. But autonomy doesn't mean that there's not a person in the system. Think about all the things that we do today that are autonomous, but we don't really think about them that way. Let's think about drones, for example. Why are drones so popular now when we've had RC planes and helicopters and such for 30 or 40 years? But why now? What's making them popular? Well, I would argue what makes them popular is that I can just grab a drone and I can push the stick forward and the drone goes forward, and I pull it back and the drone goes back, and anybody can do it. Well, what's happening behind the scenes is there are autonomous systems on board the drone that keep track of the pitch of the blades and the wind and the engine speed and all that sort of stuff. So those things are happening. I'm still in control as a human. A person is still controlling the drone, but autonomous systems are in the background manipulating the drone. We have these systems today for a long time, right? Think about your braking system in your car, right? For the anti-lock brakes. You push the brake down in your car, but that doesn't really make the brake stop. The computer then decides, based upon the travel conditions, whether it's going to pulse the brakes or whether it's actually going to apply the brakes. That's an autonomous system on the braking level that enables average drivers to drive in conditions that they may not be trained on, snow and ice and rain, right? So that's an autonomous system. And so we have lots of examples where we're thinking about these things in ways that can make the human more powerful, can take that human operator and do things that they may not have been able to do on their own. Over here we have the Sarcos Guardian S. It's the snake robot that's driving around the track and climbing the wall. Well, if you manually operate that robot, it's got this big controller and you have some joysticks, but you're trying to articulate a number of joints, right? And that's easy for a person to do. It's like driving a car, right? You can drive your car, but if I put a trailer on your car, that becomes a whole different problem, right? And so you have lots of joints in the robots, that same problem. So if I put a trailer on your car, that becomes more difficult to drive. Probably most of us can do it. Backing up is a little bit harder. But what if I put two trailers on your car? Now it's a much more difficult problem for a human to do. You still want to back up the car, but you don't know how to articulate two trailers backing up. Well, the robot is this same example, except there's 5 trailers, right? And so trying to manipulate 5 trailers going up over the arch and over stairs becomes very difficult for a human operator. but the human operator is still in control because they can just push forward, and then when it hits stairs, it knows how to go over the stairs, and you don't have to worry about all of that detail. So this is kind of the space that we're talking about when we think about autonomous systems. So we've been thinking about this in sort of three big buckets, right? Really the goal here is to scale human expertise. We want to be able to leverage the knowledge of an expert operator and have them be able to create these AI models using reinforcement learning, which I'll show you some of that in a little bit, to then manipulate and create these things, right? So we want these people that may be expert bulldozer drivers to be able to take the knowledge they have about driving the bulldozer and apply it to an AI model. They're not data scientists, and data scientists don't know how to drive a bulldozer, and the bulldozer doesn't know how to drive AI, right? And so this is where we can help them. Really trustworthy autonomy, right? This is about being understandable, transparent, explainable, running on the secure cloud platform, things like Azure and on Windows, to be able to have these good foundation for your autonomous systems. And then real world scenarios, right? A lot of the other people that are doing things in the RL space or in the autonomous space are doing it with games and video games and real board games and things like that, which is interesting. But really we're focusing on real world scenarios, like real industrial automation and autonomous scenarios that can do things like mining and farming and oil and gas and HVAC and all of those kind of things, right? Those are sort of the scenarios we're targeting. And so I think this becomes very interesting and very relevant for a lot of people. So the 5 categories that we're thinking about first, and this isn't like the entire space, but it's a way to help you think about the problem space a little bit more. One is around motion control. This is around how do you manipulate the motion of an object. In the case that I'll show you is a horizontal oil drill, right? So how do you fly this horizontal oil drill underground as if you would fly a drone in the air, except I'm flying it through, for example, shale rock, right? Our smart building scenario is very interesting. This is around how do you take a very complex system like modern buildings that have all sorts of sensors and apply an AI model that can train that to be more efficient. And I'll show you the demo of that later. Machine calibration, we have a lot of scenarios where, imagine a CNC machine, right? So how many people know what a CNC machine is? So a 3D printer will build something by adding material. A CNC machine builds things by taking material away, right? Is a good way to think about it. But over time, those blades, as it cuts, get worn out, and then the machine gets out of calibration because it needs to be in a certain spec, and the blade's smaller, so it gets out of calibration. Normally, that happens, and people stop, and it takes them a few hours to recalibrate the machine. We can do sort of what we think of as continuous calibration, where the AI is driving the calibration so that it continually stays in calibration. Process control, when you have complex processes, maybe you have, think about that like managing the luggage at the airport, or you're producing some product like maybe shampoo and that chemical process that you have to get all those in right, we can make that process a lot more better with autonomy. And then finally, this is sort of the canonical example and what we've been showing at the booth, which is industrial robotics, right? And so the point of all of these things is to make you think differently about, when we're talking about autonomous systems, we're not talking about autonomous robots or autonomous trucks or autonomous planes, but the whole system itself. And so think about that system could be a component like the brake system of your car, a blade on a bulldozer. It could be the whole thing, maybe a floor washing machine could be autonomous. It could be something simple like an autonomous greenhouse, right? Where the greenhouse has sensors that can sense and perceive the world. It can open and close the windows and turn on the fan. We think of that as an autonomous system as well. So when we think about these, it's more than robots, although robots are pretty cool though, right? Now here's sort of the tool chain approach to how we would build the intelligence for these devices using machine teaching. So the first piece we have is an expert. So you have some expert that can work with your data scientist to craft the training. It's written in a program called Inkling. So you create this Inkling file that codifies basically your information about the problem, what the lessons are, how you decompose the problem into smaller steps. Because when we're doing something like the robot manipulating a block, we don't teach the robot to take the block and build a house, right? There's lots of steps in between. And this is where the expert can come in and decompose those steps into smaller things, right? I think the classic example we've been talking about is about teaching your child how to hit the baseball. Like with traditional machine learning, you may send them out in the backyard with a baseball and a ball and say, there's a baseball and a ball in the backyard, go figure out what you want to do. Or maybe you could sit them down in front of YouTube and watch Major League Pictures hitting baseball and say, hey, here's millions of videos, go learn how to hit the baseball, right? But that's not really how kids learn, right? You learn by breaking the problem down into smaller things. Okay, first I'm going to teach you to swing, then I'll put the ball on the tee, and then I'll teach you to hit it from the tee, then I'll throw it underhand, right? Each one of those become a discrete learning that you do, in essence, in your file that you define to set up your model. Then once you set the model up, you're ready to begin training. Now, the way that reinforcement learning works is that it's based on a reward system. So when you do something right, you give the system a reward, and then when it doesn't right, it doesn't get a reward. And over time, the system learns to maximize the rewards, right? Because it wants to end with the highest reward. Now, the way this works is that you would, in simulation, create an environment where you can simulate your real-world happenings. And then in that case, you pass the state information. So here's where my robot is, and here's where the stairs are, right? Imagine you were trying to teach the robot to move to the stairs. So you say, here's the robot, here's the stairs, so the goal is the stairs. That's what you would have defined in your teaching file. So then at that moment, you pass that information to the brain, to the model here, and say, hey, here's where I am. And then the model will return an action to you, say, hey, move left. In fact, it'll really be a vector, right? So I'm going to say move left at this speed, right? But it's say, hey, move left. So then you do that action in simulation and then evaluate what happened. Was I closer or farther away? So this is where you generate the reward. Okay, +1, I'm getting closer to the stairs. And you continue that process until the robot reaches the goal, which is to arrive at the stairs. So does anybody see a problem with this process so far? So the difficulties in this system are really evaluating what the reward is. Because, you know, kids, right, if you incentivize them the wrong way, they're going to try to maximize the reward. Or how many people here have been creative with their scorecard for sales in their company, right? When you have a scorecard, you try to say, well, maybe this is included. So you're really gaming the system here. So for example, when we were training the snake robot to go to the stairs, you would get the points, a maximum number of points when you reach the stairs. So what the robot did was it came up to the stairs, didn't quite get there, got a lot of points, and then did a loop around the stairs to get more points and just kept circling the stairs. Because it learned, hey, I can get a lot of points if I just keep going around the stairs. But that's not what we were going for. So you have to kind of think about what you're trying to teach it and what the reward structure is. So that's an important step. Once that's done, and you do this in simulation because you can scale and you can simulate events that may never occur or are dangerous or different environments, you can do all that in simulation. Once you're done, you can take that model and deploy it to the edge and then run that same process on a real device. So in that case, that's what's running over there on that device. We've deployed it to the device, and it runs right on the device where instead of getting reward now, all I'm doing is saying, here's where I am, and tell me what to do next. And it says, okay, now go left. And it's, okay, now here I am, now go right. And that's what's happening. And this process here is like in gaming. It's a game loop. You want to do that as fast as you can. You want to do this 60 times a second, right? This is what you want to do when you're doing this in real life. And so we have 3 scenarios that you can do here. And you can actually go do these right now at ak.ms/asdemos. And try these. And I'm going to show you these, what these look like, so you know. So here we have the 3 demos. Let me go back and show you what these look like. So these are awesome. These are awesome, actually, demos. These really teach you conceptually what you're doing here. And this is one, the smart building example. We want to be able to maximize the comfort and quality for the people while reducing energy costs and reducing wear and tear on the equipment. And in which case we have lots of variables. This is the state information. You can imagine in a real scenario you'd have dozens, if not hundreds of variables that you would pass as your state. But here we simplified it and have just a few. So we pass these variables to the state and say, okay, now here's the temperature, what do I do? Here's the temperature, what do I do? And it would return some action. You know, open the window, close the thing, turn the fan on, and turn the heat up, right? Like that may be the action that it returns. Then you say, okay, now it's still too hot. And then so you keep going through that process, right? So this is what we do here. And what you can see in the system when you're training the system, you'll have a number of the variables coming in. You can see your CO2 levels, you can see your energy consumption. And as you go through each run, we call these episodes. An episode is a series of iterations. So an iteration may be one loop, right? An episode may be, I'm going to train it to go from here to the corner. Excuse me. And so you can see over time, it's starting to maximize the reward. Sorry. And then in the end, once you have the trained brain, hopefully it'll operate at a more consistent rate than maybe an expert operator might. Another really great example here is this one around motion control. And here in this case, what we want to do is we want to be able to stay inside of the oil pocket, inside of the plan that's been defined, and we want to go as fast as we can, right? And the reason we want to stay inside the plan is that the plan is something that's defined by a scientist. He says, okay, stay here at this depth because it's 3D space, right? Because you want to avoid other people's property, or maybe you don't have land rights, or maybe there's a natural boundary, or maybe there's other pipes or wires underground. So you want to stay here. And so this red line represents the true plan that we want to do, and the blue line represents our sort of training path. Now what we do here is in the beginning we start at a random distance and location, so then the robot, the drill head, has to figure out how do I get back on path. And then over time, as it goes through these episodes, you can see that eventually we found the optimal kind of solution, and the reward function flattens out, and we know that we're trained at that point, and we can deploy the model. And so in the end result, we end up with a more precise and a faster solution to drive that oil head. Finally, the last piece of this I want to talk about is really simulation. And simulation is so important to this process because of the things I talked about earlier. You can do things and test scenarios that may not exist in real life. But not only that, like if you're testing on your real robot or real device, those things have physical limitations to the number of cycles, right? Your robot runs for X number of hours before it breaks. So you don't want to break your expensive equipment testing it. So you run it in simulation. Also, the other thing about simulation is in real life, in IRL, for you younger kids, in IRL, time is 1 second equals 1 second, right? So if you want to train for 1,000 hours, you got a lot of overtime coming. Here, we can train it where we have hundreds or thousands of simulators spun up at the same time, and we can train in parallel at a much faster rate. And all sorts of simulators. Right now in the marketplace, there are hundreds of simulators for every vertical, and the healthcare industry has simulators for every part of the body. The oil and gas has simulators for everything. Electrical engineering has simulators for everything. We have simulators for things like drones and vehicles. And so all of these are simulated systems that can be applied to, not good. That we can see here, this case, this is AirSim. This is our first-party simulator for doing drones and vehicles. You can use either Unity or Unreal Engine to build these. Import your scenes, just like you would any game. You can just import standard environments and simulate all of these environments directly inside of the tool and generate training. So you can imagine, like I said, it's like a game, right? Every frame, you're sending the current state to the AI model, and it's telling you to move the car left to right or the drone up and down, and you do that in this simulated environment. And so here you can simulate things like traffic. You'll be able to do lighting conditions. You can also take photos of these objects in here too and use those as training your vision systems, right? So if you want to also capture images for the vision system, you can do that as well. We can do things like snow, environmental conditions, wind, leaves, all sorts of different weather that you wouldn't be able to simulate necessarily unless you hang around and wait for winter again to simulate your car. So we can do all of these things in the simulator, and it makes it really, really good. We can also simulate things like sensors, right? So if you want to test out sensors, in this case LiDAR, if you want to test out a sensor, you could test out sensors in here. You can get different perspectives. Maybe you want to see what the driver sees and have train the vision system or the AI model from that. We can also look directly down. We can also have multiple actors. So we think of this as fleets or swarms of robots or devices, right? In a factory, you may have multiple robots on an assembly line, or you may have a whole fleet of window washing robots that you send out to your building. We can do this working with a customer to do windmill inspection, so we can also train it how to get close to the windmill. And finally, just want to leave you with some links. You can go to ak.ms/as to get the main webpage, and all these will come from that. But if you want the direct links, you can sign up for the preview. So if you want to learn how to do this yourself, you can go to that link and sign up for the preview. The demos that I just showed you, those 3, you can go explore those in more details. Learning, we have a full learning course that we just released that teaches you at a 100 level, 200 level, what is machine teaching, what is reinforcement learning, what is simulation, how does that work, what is autonomous systems. So all the things I kind of talked about today in more detail. And then finally, you can try out some of these yourself with the lab. So if you go to the lab, you can download some of the source code that I built the demos with and run those. With that, thank you very much. And if you have any questions, please come up front.